All right, so the final video for this class, section 11.3, and this is going to be the law of cosines. Now, your suggested exercises are 5, 7, 9, 11, and 17. And if you need to peek at the answers, that's okay, because again, I'm not forcing you to use, or I'm asking you to not use a calculator on assessments in this class. So if you're not used to plugging things in, it's worthwhile to practice and make sure that you can get the correct lengths by plugging in the trig formulas. Anyway, the big ideas are going to be, of course, the law of cosines, which is going to be another law kind of like the law of sines, but also we're going to learn a notion called semiperimeter, and we're going to learn about what I believe is called Heron's formula. I read it before I heard it, so I always say Heron's formula, but I believe it's pronounced Heron's formula. And then I'd like for you to look at examples 1 and 3 in the book. So let's dive right in. The law of cosines basically says, with the triangle like we had before, so side lengths A, B, and C, and opposite angles alpha, beta, and gamma. So a triangle with side lengths A, B, and C, and opposite angles alpha, beta, and gamma, we have, I'm going to give you 3 formulas, but they're all going to be based on this one. So the one that I like to remember is c squared equals a squared plus b squared, which looks familiar, but we're not done yet, minus a correction, minus 2ab cosine gamma. So this looks like the Pythagorean theorem, a squared plus b squared equals c squared, but we've got this extra factor here, and the idea is if gamma is 90 degrees, what do we have? Well, let's draw our triangle in here. I'm going to make it look almost like a right triangle, but not quite. Okay, so this is going to be gamma. Here's c. This is a gamma. Oh, goodness. So I've got a opposite of alpha. Got b opposite of beta. So if gamma was 90 degrees, then I would have a right angle here, and we'd have the Pythagorean theorem, right? And if gamma is 90 degrees, then this goes away. But if gamma is not 90 degrees, then we need that correction factor in there. So this is a more general Pythagorean theorem, which is, a squared plus b squared equals c squared, but then there's some wiggle that we need to fix out, and that's this term here. Now, like I said, this is one of the 3 ways to write down the law of cosines. The other ways being, of course, b squared equals a squared plus c squared minus 2ac cosine beta, and a squared equals b squared plus c squared minus 2bc cosine alpha. This is how these work. Another thing that I want to mention in this section is the triangle inequality. And I like to denote the triangle inequality a triangle on top of a not equal sign. The triangle inequality basically says in any triangle we have the sum of any 2 sides must be greater than or equal to the length of the third. So in our case, we've got a plus b is greater than or equal to c, a plus c is greater than or equal to b, and finally, b plus c is greater than or equal to a. Now, this inequality is powerful and it says a lot more, but basically why I'm giving it to you right now is if I say, solve the triangle, with side lengths 1, 2, and 10, you can't. Okay, there's no solution, and this is because it violates the triangle inequality. And just a little bit of a picture here. So what are we saying? Well, imagine that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's a side of length 10, then I don't know which direction my one length side is going to point, but I know that it can reach no farther than this circle of radius 1. And I don't know which direction this 2 length side is going to point, but I know it can reach no further than this circle of radius 2. I know this kind of looks like the bicycle from before, but the idea is no matter what I do, there's no way to match up this side to this side. We can't make them meet at a point. That's because we're violating the triangle inequality. The reason I mention this is because we can use the law of cosines to solve triangles, but we'll get that things come out funny. So if I try to use the law of cosines here with A, B, and C, then I'm going to get a cosine of an angle that can't be. I'm going to get a solution for this, which is the cosine of some angle is outside of the range of a cosine. So let's see what we mean here. Let's just plug this in. Let's suppose that this is A, B, and C. So this is the easy way to see it, like this, quote unquote easy. The hard way is to plug in the law of cosines. We get that 10 squared equals 1 squared plus 2 squared minus 2 times 1 times 2 cosine of whatever the angle opposite of 10 is. Well, let's do a little bit of arithmetic. We get 100 equals 3 minus 4 cosine gamma, which tells me that 97 equals 4 cosine gamma, which tells me that cosine of gamma has to equal negative 97 over 3. But that is much, much less than negative 1, which is the minimum value of cosine, so no such angle. Okay, and basically either way we get to no solution. Okay, so I know it's a little weird to start off by giving you a non-example, but I just want you to be wary that I could give you, a triangle inequality question that doesn't have a good answer. A law of cosines question that doesn't have a good answer. Okay, but instead of doing that, let's do a law of cosines type question that does have a good answer, or at least a manageable answer. Let's say solve the triangle with A equals 2, B equals 3, and C equals 4. And we can see here that 2 plus 3 is bigger than 4, 3 plus 4 is bigger than 2, and 2 plus 4 is bigger than 3. So this satisfies the triangle inequality. So solution, we begin with a law of cosines. And it really doesn't matter which one we do, but I'm gonna do the c squared equals a squared plus b squared minus 2ab cosine gamma. And when I write that down, this tells me 16. Oh, I guess I should write 4 squared equals 2 squared plus 3 squared minus 2 times 3 times cosine of gamma. So we're finding gamma here. Let's simplify this. So we've got 16 equals 4 plus 9 minus, now this is 4 times 3, so minus 12 cosine gamma. What do I have? I've got 3 equals, because this is 13 from 16, 3 equals negative 12 cosine gamma. And this tells me gamma is cosine inverse of 3 over 12, which is of course cosine negative 3 over 12, which is of course negative cosine inverse of negative 1/4. And I could compute that, but I'm going to go ahead and leave that there. Now there's a subtlety here, which is that gamma could be, so what do we want? Draw our unit circle. We know that cosine of gamma is 1/4. So my angle could be this one, or it could be this one, right? But we know that the sum of the angles of a triangle are 180 degrees, so it's not going to be bigger than 180 degrees. So it's going to be whatever this angle is here. All right, so not to worry. Next, we can use the law of sines. And so I can actually use the law of sines to find alpha and beta, but I'll just use it to find one. Let's say the law of sines. Now we have that sine alpha over A equals sine gamma over C, because this ratio holds for all A alpha, B beta, and C gamma. So now I have sine alpha over 2 equals sine, and I'm just going to leave this, I'm going to call it gamma until I actually have to use it, over 4. And then I'm solving for alpha, so I have sine alpha equals 1/2 of sine gamma. Now, because I know that gamma is cosine inverse of 1/4, I could compute the sine here. I'm going to go ahead and not do that, just because, in the interest of time here and saving a little bit of space on the page. So we'd have sine of cosine inverse of -1/4, and we could compute this, and it would be really fun. But I'm gonna say that alpha is going to be then sine inverse of this. So I have that alpha is sine inverse of 1/2 the sine of cosine inverse of -1/4. And this is getting quite nasty, right? So you are more than welcome to just leave this as gamma, since we've already found, to leave this portion as gamma, since we've already found gamma here. All right, and finally, we know that alpha plus beta plus gamma equals 180 degrees. So we get that beta equals 180 degrees minus alpha, which I'm just going to say is this thing, and minus gamma, which I'm just going to say is this thing. So I'm not going to rewrite those. And I'm going to call that my final answer. Okay, again, like I mentioned before, occasionally you end up with these situations where there's potentially more than one angle. Like here, this alpha, what's the y value here? Well, we could get sort of complicated things coming out of it. Again, I don't want to read too much into this. I want you to have a basic idea of how this works. And if you end up having to use this at a very high level, then you're going to learn about when you might need to find more accurate answers, when to plug things in and check and say, oh, well, I've got two possible triangles that could come out of this. But I'm not going to be pushing us too hard on that for this class. So the last thing I want you to see is for a triangle, well, I'll just write it like this: the area of a triangle with side lengths A, B, and C is the square root of S times S minus A times S minus B times S minus C, comma, so I'm not ending a sentence yet. So I haven't told you what S is, so this is where I say where S equals A plus B plus C over 2, the semiperimeter. And this right here is called Heron's formula, or Hero's formula. I guess I should have introduced that. All right, so let's do a quick example. Find the area of the triangle with side lengths 4, 5, and 6. So solution, first let's compute S. S is the semiperimeter. We just add them up and divide by 2. 4 plus 5 plus 6 divided by 2 equals, that's going to be 15 over 2, or 7.5, whatever. And then A equals the square root of S times S minus A times S minus B times S minus C. And for us, that's going to be the square root of 15 over 2, then 4 minus 15, 15 over 2 minus 4, 15 over 2 minus 5, and 15 over 2 minus 6. And, this is a fine answer. We can stop here, or we can simplify it a little bit further if we'd like. We get 15 over 2, so Now I'm subtracting 8 over 2, so I've got 7 over 2. Now I'm subtracting 10 over 2, I'm left with 5 over 2. And now I'm subtracting 12 over 2, so I'm left with 3 over 2. And we've got, what is this going to be? I can pull out 15 over 4, and I'm left with the square root of 7 is what it looks like to me, unless I've made a mistake. Anyway, the point is we can use this to find the area of a triangle with its side lengths, again, without requiring that we have a right triangle. So the formulas for areas of triangles that we have are typically, 1/2 base times height. But if I don't know either the base or the height, if I've got some weird triangle that's not a right triangle, and I don't know that height, well, then I can't use that 1/2 base times height formula. So this helps us deal with triangles when we don't have that information. Okay, well, thanks so much for watching.